Okay, we're going to knock out the tutorial now. So, for today's tutorial, the goal is just to get better at actually solving these differential equations using the Laplace transform. So, here we have 4 different problems to work through. They all have their own little differences to it, but mostly this is just to get you in the habit of actually solving these pretty efficiently. So, without further ado, let's start on the first one. So, what I'm going to do is I'm just going to grab the statement from here, and we're going to try OneNote. There we go. Okay, so if I want to solve this guy, the first thing I need to do is apply the Laplace transform to everything. So, Laplace transform being applied to the differential equation, what happens? Here I'm going to get a minus 2. Y prime corresponds to y, our s, capital Y of s, minus the initial condition, plus my y of s, that being the Laplace transform of the y. Laplace transform of 0 is 0. Yep. So now the goal is solve for y and apply initial conditions. So initial conditions, this comes out as a 1. So here I have a minus 2s plus 1. This is the thing in front of my y of s, is going to be equal to, so I have a minus 1 times negative 2, so that's 2, subtract it over, I get a minus 2 over here. So now I simply isolate this guy for my y, and then I look to see, is this in my list? And if so, which rule is it? Minus 2s plus 1. Okay. So now I check my Laplace table and see if this is to be found. So if I pull up a thing with a Laplace table, I'll just do that on the side. There we go. So if I pull up our handy-dandy Laplace table, this isn't directly in our table, but it can be derived from our table. All right. So here I don't have a rule for 1 over negative s plus 1. Right. I don't have that form. This, out of all these forms, it's not like an s squared, so it's going to be none of these. But it is a regular s, so it's going to be like a t to the n kind of thing. Yeah. So 1 over s corresponds to Laplace transform of 1. So if I look at this top rule, if n is equal to 1, I end up with Laplace transform of 1 is just 1 over s. So this looks kind of like this, but I have not quite there. So my options are try to see if I have rules to do all of this, or see if I can do some shenanigans to put it in a standard form. Now, we've seen things with the s plus 1 multiple times before, and we noticed that those were exponentials, right? Some Laplace tables even have that as a list, or as one of the elements of the list. If I look here, I have this exponential modulation that says if I gave you something like the inverse Laplace of 1 over s minus alpha, that kind of looks like our form, then this would be e to the alpha t, and then the 1 over s minus alpha, well, that'd be that multiplied by my Laplace transform of this without the alpha, but that's just a 1 times 1, right? So this looks like an exponential, but I still have the minus 2 in front of the s, right? One way I could handle the minus 2 in front of the s is by doing time scaling, right? I could say, well, this is s divided by negative a half, and I could clean that up. But time scaling really is, in this context, not super needed, because I can just do that algebra manually, right? So here's what I would recommend for this one. I could rewrite y of s with all of this stuff that we just noticed. I could rewrite it as my minus 2. Here I have my minus 2s plus 1. I could multiply the top of this by minus a half and the bottom by minus a half. Right? That'll give me a coefficient to 1. It's literally doing what time scaling tells me to do. Right? So here, the top, I'm going to get a 1. in the bottom, I'm going to get a s minus 0.5. Right? And from here, I can now just say, well, this tells me y of t is going to be just my exponential, e to the minus 0.5 t. Yep, so that's all there is to this. Plus 0.5 t, not minus. Where are we? There, plus. So that's all there is to it. The question statement for this said to go verify that it works. If I wanted to do that, what I can do is I need to check, does this solve the differential equation, and does this satisfy the initial conditions? Those are the two things I have to check. So if I just take it and plug it in, I would get 0. Right? Derivative of this, I pull out the half cancels with the 2 to give me a minus 1. Yep. And if I plug in 0, I do get 1. And so it's always good to do those checks because they're generally not overly hard to do. And yeah, so that's it for question 1. Again, the things to keep in mind when doing these kind of things are these computations are the types of things that you want to look for in trying to figure out how to rewrite your expression to make it convenient. Whether that be doing a weird partial fraction decomposition ansatz, or doing the thing with the derivative that we've seen a couple of times now. That's kind of the creativity aspect of the problem, and it can really change a question from being easy to being a really hard problem, depending on how you choose to approach that aspect of it. Okay, let's do number 2. So let me just clear up things. Okay, so for the second question, what they're really asking us to do is to compute or use Laplace transform to solve this second order ODE. So effectively, what we want to do here is exactly the same mechanical steps that we just did, just with a new DE. So here, if I were to actually take Laplace transform, this guy is going to give me a s squared y of s minus s little y of 0 minus y prime of 0. That's just the y second derivative term. Minus 2. Here I'm going to get s y of s minus y of 0. Then I'm going to get a minus 3 capital Y of s is equal to 0. Now I apply my initial conditions, right? So the initial conditions tell me that this is going to be 2, that this is going to be 2, and that this is going to be minus 1. All right, so now I just want to group things up. So when grouping, you're always going to end up with the characteristic polynomial multiplied by your y of s. That's just the way that, well, you can prove that that'll always be the case, but it's literally just coming from the fact that my derivatives give me a s to the n y of s, and I'm going to pick those terms up from here. So I get this guy minus 3, all of this times y of s is equal to, I can pull these other terms over. So here, I'm going to get a 2s. Here, this gets me a plus 1, so I get a minus 1 when I pull it over. Here, I get a minus 2 with the 2, with the negative, so I get a 4. When I pull it over, I get a minus 4. And that's it. So I can clean this up. This guy gives me my minus 5. All right? So now I can divide through by my characteristic polynomial. So I do need to factor it for doing things in a bit, but I can write this as 2s minus 5 over. Now I think, how does this factor? All right. Well, I can do a s. I have a 3 and a 2. I need a minus 3 because it needs to be bigger than the 2, and I'm going to get my s plus 1. All right, negative 3 times 1 gives me this. If I add them, I get that. So here I'm going to have a s plus 1. S minus 3. And I'm sad that I don't get cancellation, but now that I have this, we can do our partial fraction decomposition. Now, in this case, I want to always keep in mind, what do I have in my in my Laplace table when doing this partial fractions? So here, default, I would have there's the cursor. I would have a s plus 1 term and an s minus 3 term. If I look at my Laplace table, in particular, the shenanigans I just did, we know Laplace transform of e to the alpha t, there we go, is going to be 1 over 1 minus, s minus alpha. Yeah, so we have this one from exponential modulation applied to 1. So these are just going to be flat out exponentials, so I can use the standard guess, right? If I figure out what a and b are, it's going to be a times e to the negative 1t plus b times e to the 3t. Yeah, so to match these, I just do the cover-up method. So I get 2s minus 5 over my s plus 1, s minus 3. Yeah, so the way cover-up method works, I'm going to do it in highlighter here. I multiply through by s plus 1, so this goes away, and this will go away. This guy will pick up an extra s plus 1, right? Then if I plug in the root of that, so if I plug in 0, then the things that I just highlighted will disappear. And I can just get a is going to be equal to 2 times 0 minus 5 over 0 minus 3. So that's just going to be 5 over 3. Right, so I can just read it off. Now if I do it the other one, right, if I multiply through by this, then this term vanishes. The whole term here would go away. And then if I were to plug in 3, and by plugging in 3, I get b is going to be 2 times 3 minus 5 over 3 plus 1. Right? So you just do your little arithmetic. I get 15 minus 5 gives me a 10 divided by 4. So 10 over 4, which obviously you could simplify to 5 over 2 if you wanted, but there's my b. Yeah, that's all there really is to these kind of setups, is you build up, get your coefficients, use your Heaviside cover-up method to actually compute the coefficients, and you're good from there. Okay, now if I can actually do arithmetic here. 5 times 2 is 6, so I get a fourth, not 10. Okay, we'll fix that thing. There we go. Okay, good. So now, I just put it together, right? Scroll down. Okay, come on. Yeah, there we go. So, putting all this together, I get my y of t. Oops. Of t is going to be equal to, I'm going to get my a, so I'm going to go 5 over 3. Looks like I messed up my a too. I butchered that. If I was a better human, I'd go do editing too. So if I actually go through here, for a, I would plug in -1, because when I plug in 0, I don't get a root. So if I plug in -1 to actually get the real a coefficient, there we are, I'll get a 2 times -1 minus 5 over, this term would be gone. I end up with a -1 minus 3. Here, I get a -2, so I get a -7 over 4. But both are negative, so I just get 7 over 4. Good. Okay. I can do arithmetic at 7 in the morning. Good. Good. Okay. So we get 7 over 4 here. So I apologize for that. Algebra, I just plugged in the wrong number. Okay, so now I get my 7 over 4. Okay. U. So now I get my 7 over 4. Inverse Laplace of the a term is going to get me e to the minus t. Then I'm going to get a plus 1 over 4. Inverse Laplace of the b term will give me e to the 3t. I get this guy. And if you want to check it, right, you know what the fundamental set is. The fundamental set for the DE is going to be e to the negative t, e to the 3t. So my proposed solution is a linear combination of those. Therefore, it will solve the differential equation itself. And then if I want to test for the initial conditions, all I do is plug in 0 and see what we get. So if I plug in 0 for t, I get 7/4 plus 1/4, 8/4, that is 2. And if I plug in, take its derivative, and then plug in 0, here, for the first term, I'm going to get negative 7/4. For the second term, I'm going to get 3/4. If I add those together, I do get negative 1. All right? So we can check that I computed the coefficients correctly by doing that. Yeah, and it's always good to do that because small little algebra errors like the ones I just did when computing A, right, can sometimes result into pretty heavy issues down the line. For this case, it doesn't. It'd be like a half mark error. You did everything, you just computed A wrong, right? But just keep that in mind. Okay, let's knock out question 3. So question 3, we're going to apply the exact same method, right? Just different difference equations. So I'm going to wipe my slate and go from there. Okay, now we're back. So same type of thing, just some details change, right? Here, the only details that are really going to change are the characteristic polynomial. Most of the stuff's the same, but this repetition is actually good for the act of learning. So if I take Laplace transform of everything, I'm going to get my s squared y of s minus s y of 0 minus y prime of 0 plus 2 s y of s minus my y of 0 plus 2 y of s is equal to 0. Applying the initial conditions, this gets me minus 1, this gets me a 2, this gets me a minus 1. Okay, so now that I have that set up, I just solve for my y again. So here, I'm going to get, again, characteristic polynomial, s squared plus 2s plus 2 y of s equal to. So here I get a minus s, so plus s, so I get a minus s when I bring it over. Here I get a minus 2, so a plus 2. Here I have a minus, so this gives me minus minus, so a 2, so I get a 2 here. This guy canceled. Yeah, these two cancel. Good. So then I get a minus 2 here. These cancel. So I just get the minus s. Good. So now that I have this, I want to divide through by the denominator, but unfortunately, this one doesn't factor particularly nicely, right? So I want to try to figure out how can I make this of the form of something in my list. Plus 2s plus 2. All right, since it's not a perfect square, since it's not of the form, let me just get my whole, there we go. There's the positive. Since it's not one of these, right, I can't use those formulas, obviously, but since I have s squared plus something, I can't do the exponential trick either. So it's going to be kind of somewhere in the middle. There's going to be maybe some exponential, maybe some of this. Turns out that the trick that I can do for these is to complete the square. If I complete the square for this denominator, then what I can end up doing is I can rewrite it where part of it will be an exponential modulation and another part will either be sines, cosines, tangent, or cosh, depending on the numerator and the details of whether or not I get a plus or a minus. So here's how completing the square works. So s squared plus 2s, I could add something to this that I will also subtract and plus 2. The idea is I want to add and subtract something so that this part becomes a perfect square, right? And you can sometimes eyeball it. The general trick is you take the number that's in front of the s. Oops, there we go. You take this number, you divide it by 2, you square that. That's what you add. But here you can see I need to add 1, subtract 1, right? If I do that, this first part becomes s plus 1 quantity square. and the second part just becomes a plus 1. Right? So doing this, I could rewrite this whole thing as minus s over s plus 1 squared plus 1 squared, if you want to put it exactly of the form. So this looks like our sine cosine formulas. In particular, it looks like the cosine formula, but I have an s plus 1 instead of an s. The way I deal with the s plus 1 is always exponential modulation. But to apply exponential modulation, I need to have an s plus 1 everywhere where s appears. So this means this s that I have up here needs to have a plus 1 attached to it in some way. Right? So now what I can do, I'll just scroll down here, is I can rewrite this and say, well, y of s, there's my, sorry, no, this, bring this down. I can say my y of s is going to be, I want a s plus 1 over s plus 1 squared plus 1. I'm just going to drop the square. I want this to look like this, but I currently have a minus s, right? So I could do this. Now I get my minus s, and I could add a 1 back. Right? So what I'm really doing is just adding and subtracting 1 in a way where I can make this look like something in my list. Right? This is now going to be negative cosine if that was just a regular s. So I can split these guys up. Right? Negative s plus 1 over s plus 1 quantity squared plus 1 plus 1 over s plus 1 quantity squared plus 1. Right? These are now legitimately in my list. So if I go take the inverse transform, this one, I'm going to get negative, because the negative here. To deal with the s plus 1, I'm going to pull out an e to the minus t. And what I'm left with, I'll just write it here, is the inverse Laplace of s over s squared plus 1. Right? Plus here, I can pull out my e to the minus t. Right? And in this case, I'm left with the inverse Laplace 1 over s squared plus 1. Now, I can just factor out my e to the minus t. This is going to be minus from the negative out front. This one's cosine. This one's sine. Done. Yep. So the trick is, once you've factored the things out, you try to look for stuff that looks like things in my list. So these, if you've got them, and if those aren't there, then you go for the exponential, right? And if neither of those are there, then you go for a combination of exponentials with these, right? So the indicative factor here that I should do completing the square is literally the fact that this is a quadratic. So it's either going to be like these guys, or maybe 2 exponentials, depending on how it factors, right? So since it's quadratic, if I do completing the square, I can separate out the exponential bit, this guy, from either the sinh or the cosine bits, depending on whatever the sign is, right? So that's the indicative factor there. Once I get that, then it's, well, this isn't in my list. I need a plus 1, get a plus 1, but I have a negative, so I technically need a minus 1. Then I do the add and subtract trick. You could also do it with completing the square, or partial fractions. They'll get you the same thing, but here, arithmetic works, so try to do the thing that's the easiest to do. Okay, so we will look at the last problem in a bit after I clear the slate. Okay, and again, in the last example, I didn't do this, but you can check your answer. The question said to check it, but just computational. Mostly there so that you have some experience of checking your answers so that you can verify if you're right. That's always kind of nice. Okay, so here we want to do the same type of thing we just did, but we're now going to have a forcing term, so we need to deal with the Laplace transform of the first forcing term as well. And here we're lucky that 3 isn't going to be a root of the characteristic polynomial, if you just kind of eyeball it. 3 is not going to be a root of the thing I get from here. Therefore, I'm not going to get resonance. So it's going to be not a horrible problem. Right, so I get my s squared, capital Y of s, taking the Laplace transform of my y double prime, minus my sy0, minus my y prime 0, minus my s y of s, minus y of 0, minus my 2 y of s is equal to, from the table, this is just 3 over s squared plus 9. Right? Apply initial conditions. This guy gets me a 1. This gets me a 1. This gets me a minus 1. Factor out to solve for y. Again, you can actually do all the solving for y computations in one line, but I suggest against it just because it increases algebra errors, right? You're more likely to drop a -1, things like that. But if I factor these out, these 3 terms, I get my characteristic polynomial times y of s. Here, on the right-hand side, I'm going to get my 3 over s squared plus 9, and now I want to bring these terms over. So I'm going to get a plus s coming from that -1 y naught. I'm going to get a -1, so it's a positive 1, so it becomes a negative to get it to the other side of the equation. Here, I get a -1, so it's a positive 1, so I get a 2, get a 1, so this guy. These together give me a 2, and then that's it. All right. So from here, now I want to divide through by this guy. Y of s is equal to, here, does this factor? That's kind of the question that we should check. Here I can get a s plus 1 and a s minus 2. Right? 2 times, -2 times 1 gives me the 2. If I add them, I get my 1. So here, if I put these together, I get 3 over s plus 1, s minus 2, s plus 9, s squared plus 9. There we go. So I get all of these guys. For these other terms, I'm going to get a plus s minus 2 over s plus 1, s minus 2. All right. So now I want to start thinking about how to take the inverse Laplace transforms of these. And part of that is, are there any simplifications I could do that make the problem a bit nicer? And to the answer to that, this term and these terms cancel, right? So I can tell you immediately that this guy, when I go to take its inverse Laplace transform, is just going to give me an e to the minus t. All right, that's kind of nice. Now I have to deal with these terms here. Dealing with these, the natural way to kind of break it down is the s plus 1, s minus 2, s squared plus 9. And those will correspond to 2 exponentials, and then either sine or cosine, depending on what happens with the numerator after I do the partial fraction decomposition. So here's where I just do my partial fractions. So I get 3 over s plus 1, s minus 2, s squared plus 9. And the ansatz I want to use is going to be the one that's compatible with my table, so I don't have to do any post-processing. So a over s plus 1, that'll give me my a times the e to the negative s, or negative t, which matches this guy, plus my b over my s minus 2. So this will give me another exponential, plus here, s squared plus 9, I have shenanigans to do. Generally, cs plus d would be the normal go-to guess. But here, since this is a 9, in my Laplace table, I need a 3 up above, so I'm going to call this 3d, so that this term will be, the last one, will be c times cosine of 3t plus d times sine of 3t. All right? That's just to make things a bit cleaner there. Now I do my Heaviside method. All right, so A, I can read that off immediately. And let's see if we don't make typos this time. So A is going to be, I multiply by my s our s plus 1, and then plug in s is negative 1. So it's going to be 3 over minus 1 minus 2 times minus 1 quantity squared plus 9. Yeah. So from here, this is going to be 3. The bottom gets me a 3, so I can cancel them. So I get minus 1 over 10. Oops. Switch back here. Oops. Over here. 10. Right? So the 3, this negative 3 gets me the minus 1, and then I get my 10 coming through there. Okay, that was nice and easy. Now we do it for b. B is going to be 3 over, I'd multiply by my s minus 2 and plug in 2. So I get 2 plus 1. The s minus 2 goes away, and I end up with a s squared, which will be a 2 squared, plus 9. Yep, so here the 3's cancel, and I end up with the 1 over, so I end up 4 plus 9, 13. Oops, over here. So my b will be 1 over 13. Okay, a and b done. Now for c and d, I can use Heaviside method, but by using Heaviside method, I kind of have to instead deal with complex numbers. So your choice is deal with a 2x2 system or deal with complex numbers, which effectively is a 2x2 system, but you're guaranteed it'll be decoupled. So for so for c and d, what I'll do is multiply by s squared plus 9, and I plug in a roots. The roots of this are 3j and negative 3j. We're going to use 3j because I like being positive. So we're going to get 3j times c plus 3d, that's just plugging it on here, is going to be equal to this side of the equation, the left-hand side, when I plug in 3j and when I've removed the s squared plus 9 term. So I'm going to get 3 over 3j plus 1, 3j minus 2. Yeah. Now what I have to do is I have to do the 115 complex arithmetic stuff to rewrite that left-hand side as a single complex number in standard form. Okay, so the way that I would do it here is just multiply out the bottom. So I'll do all the details here because we've got a bit of time because there's no questions because obviously there's no in-person students. So let me get my draw. There we go. So here I'm going to get 3 over 3j times 3j will give me a minus 9. 3j times negative 2 will give me a minus 6j. 3j times 1 will give me a plus 3j. And 1 times 2, negative 2 will give me a minus 2. Right. This cleans up. Here, these, 9 minus 2 gives me minus 11. These give me a minus 3. Okay. So minus 11 plus 3j. So now what I want to do is go change color. There we go. Is I need to get the complex number in the denominator up into the numerator. So to do that, I multiply by the complex conjugate. Right? So I get minus 11 plus 3j over minus 11 plus 3j. 3j. Okay, so if I multiply by this, the bottom will just become the norm squared of the complex number. So that's going to be 11 squared plus 3 squared. Right? Now you could actually multiply it out. Negative 11 and negative 11 gives me this. The complex bits cancel in the middle. I'll get negative 3j times 3j. But it's pretty much better just to memorize that that's going to be the norm. It just takes away some of the computations, right? So now here I end up with a 3, and I'm going to leave the 3 there for reasons. 3j. Oops, j. There we go. Now notice I have a 3 on the left-hand side, here and here. So if I leave the 3 and don't multiply it out, I just get to do less arithmetic. And less arithmetic is always a nice thing. So now, the imaginary parts have to equal the imaginary part, and the real part has to equal the real part. So that tells me that my 3jc is equal to the imaginary bit here, so I can just solve. C is going to be, the 3's cancel, I get the thing in front of j, so another 3, over my 11 squared to 121 plus this gets me a 130. And my d is going to be equal to the real part over here, so I'm going to get a minus 11, the 3's cancel, over a 130. Okay, so that's how to do that setup, and that's about how long it should take, maybe a bit quick, depends on you, right? But you should be stepwise. This is kind of the like showing all your work version of it. So now what I want to do is go take the inverse Laplace, and I just read off my things. So I'm going to copy this and paste and pause so I can move things around. And there. Okay. So now if I go to do the inverse transform, I can rewrite my final solution, y of t. And I'm going to use a thicker marker because I zoomed out. It's going to be a, so a is minus 1 over 10, e to the minus t, plus b, b is 1 over 13, e to the 2t, plus c, c is 3 over 130, so I'm just going to factor out the 130, because both c and d have that factor. And I'm going to get 3 times cosine of 3t. And I'm going to get a minus 11 sine of 3t. Right? Again, I need the 3 in front of the d in order to make this transform just pull over whatever the value of d was. If I didn't put that, I would have a 33 for d, and I'd have to remember to divide by 3. You can do that. It's perfectly valid. But I found in my experience, students are more likely to make errors if they don't do that. So, again, I would normally at this point go and ask for any questions, but yeah. So now this, again, was only dealing with this term. Right? I need to add in my plus e to the minus t. Yeah. So one of the things that's very easy to do is you focus on one part that's hard and you drop the other one and then blah. So yeah, so this guy has to come back over here. Yep. I almost dropped it as well. So just keep that in mind when you do these big computations. Don't forget to go back and make sure you pick up all the pieces you need. Okay, so that is it for online version of tutorial. Yeah.